Day and 201 students, and welcome to another module of our chemistry lecture course. Module 3 is entitled The Solid State and Materials Chemistry, and will cover the structures and properties of the different solid state materials. In this lecture video, we will discuss the first section of the module regarding crystalline solids. This lecture video is developed based on the following references. You may check any of these books for further reading. At the end of this lecture video, you will be able to define and categorize solids based on the arrangement of particles as crystalline and amorphous solids. And you will be able to determine the classification of crystalline solids based on their interparticle forces as molecular, covalent, ionic, and metallic solids. Let us first define and determine the general characteristics of a solid. As opposed to liquid and gases, solids have definite mass, volume, and shape. They do not take up the size, shape, nor volume of their container. The distances between their constituent particles are short, thus resulting to a strong intermolecular forces. While liquid and gaseous molecules are free to move, constituent particles of a solid, may it be atom, molecules, or ions, have fixed positions and can only oscillate about their mean positions. As a result of these characteristics of the microstructure of solids, they are generally incompressible and rigid. Solids can be classified as crystalline and amorphous based on the nature of order present in the arrangement of the constituent particles. A crystalline solid usually consists of a large number of small crystals, each having a definite characteristic geometrical shape. In a crystal, the arrangement of the constituent particles is ordered. It has a long-range order, which means that there is a regular pattern of arrangement of particles which repeats itself periodically over the entire crystal. An amorphous solid consists of particles of irregular shape. The arrangement of constituent particles in such solid has only a short-range order. In such arrangement, a regular and periodically repeating pattern is observed over a short distance only. Such portions are scattered, and in between the arrangement is disordered. To visualize the difference in the arrangement of particles between crystalline and amorphous solids, you may have already observed it during one of your visits in the fruit section of the supermarket. The arrangement of particles in a crystalline solid is in a very orderly fashion. These particles in a crystalline solid are arranged in a repeating pattern of a three-dimensional network. This network is known as a crystal lattice, and the smallest unit of a crystal is called unit cell. These terms will be discussed in the succeeding part of this module. In an amorphous solid, the particles do not form the three-dimensional lattice structure. They have a short order to random arrangement of molecules. Again, for crystalline solids, the particles have a regular, repeated, long-range order arrangement, while amorphous solids have random arrangement of particles or only have a short-range order. In terms of melting point, crystalline solids melt at a sharp and characteristic temperature. On the other hand, amorphous solids soften over a broad range of temperature. Crystalline solids are anisotropic in nature. That is, some of their physical properties, like electrical resistance or refractive index, show different values when measured along different directions in the same crystal. This arises from the different arrangement of particles in different directions. Since the arrangement of particles is different along different directions, the value of same physical property is found to be different along each direction. Amorphous solids, on the other hand, are isotropic in nature. It is because there is no range order in them, and the arrangement is irregular along all the directions. In terms of cleavage property, crystalline solids, when cut with a sharp-edged tool, they split into two pieces, and the newly generated surfaces are plain and smooth, while amorphous solids, when cut with a sharp-edged tool, they cut into two pieces with irregular surfaces. Common examples of crystalline include all metals and some ceramics such as diamond, graphite, and sodium chloride, while amorphous solids include most polymers such as plastics and rubber, and some ceramics such as coal, coke, and glass. Calcium carbonate, a solid, has two forms based on the arrangement of particles: crystalline calcium carbonate and amorphous calcium carbonate. An example of a calcium carbonate in crystalline form is marble, and it is known to be hard in nature, which is the result of its regular and long-range order arrangement of its particles. Whereas, the amorphous form of calcium carbonate, like chalk, is soft in nature. That is due to the irregular and random arrangement of its particles. Likewise, silicon dioxide or silica can exist both in crystalline and amorphous form. Crystalline form of silica is commonly called as quartz, while its amorphous form is glass. Contrary to common belief before knowing the definition of crystals, glass is actually an amorphous solid. It is commonly used to fake crystals like quartz and diamond, thus the term puwet ng baso. Now, how do we spot whether a crystal is fake or genuine? Well, we can consider its properties. Genuine quartz would possess the properties of a crystal, while glass as fake quartz will not. When light passes through a material, genuine quartz will polarize the light, while a glass does not. Quartz will have higher density and higher melting temperature than glass. And when cut, a genuine quartz will result to a smooth surface, while streaky patches will be observed for glass. These differences are due to the fact that they have different microstructure, specifically the arrangement of particles, despite the fact that they contain the same particles. Crystalline solids are divided into molecular, covalent, ionic, and metallic solids based on the nature of interparticle forces. For molecular solids, molecules are held by intermolecular forces such as dispersion and dipole-dipole forces. For covalent solids, each atom in the crystal are covalently bonded to its neighboring atoms. In ionic solids, network of alternating positively charged cation and negatively charged anion are held together by ion-ion interaction. For metallic solids, metallic cations are held together by metallic bonding, wherein the cations are surrounded by sea of mobile valence electrons. Molecular crystals typically consist of molecules at the lattice points of the crystal held together by relatively weak intermolecular forces such as van der Waals force. The intermolecular forces may be dispersion forces in the case of nonpolar crystals, or dipole-dipole forces in the case of polar crystals. Some molecular solids, such as ice, have molecules held together by hydrogen bonds. When one of the noble gases is cooled and solidified, the lattice points are individual atoms rather than molecules. But in all cases, the intermolecular forces holding the particles together are far weaker than either ionic or covalent bonds. As a result, the melting and boiling point of molecular crystals are much lower, and they are easy to deform and compress. Lacking ions or free electrons, molecular solids are poor electrical conductors. Examples are most solid organics and solidified inert gases. A covalent solid consists of atoms at the lattice points of the crystal, with each atom being covalently bonded to its neighbor atoms. The covalently bonded network is a three-dimensional and contains a very large number of atoms. Covalent solids are hard and brittle, with extremely high melting and boiling points that they may even decompose before melting. Being composed of atoms rather than ions, they do not conduct electricity in any state. Covalent solids include diamond, quartz, many metalloids, and oxides of transition metals and metalloids. The ionic crystal structure consists of alternating positively charged cations and negatively charged anions. The ions may either be monoatomic or polyatomic. Generally, ionic solids form a combination of group 1 or 2 metals and group 16 or 17 nonmetals or nonmetallic polyatomic ions. Ionic solids are hard and brittle but have high melting points. Since the ions are not free to move about, they are electrical insulators in solid state. However, when in molten state or when dissolved in water, the ions become free to move about and they conduct electricity. Common examples are solid salts such as sodium chloride. Metals are orderly collection of positive ions surrounded by and held together by sea of free mobile electrons. These electrons, also referred as delocalized electrons, do not belong to any one atom and are mobile and are evenly spread out throughout the crystal. Each metal atom contributes one or more electrons towards this sea of mobile electrons, and these are responsible for high electrical and thermal conductivity of metals. Because of the presence of these free electrons, metals are lustrous. Metals are also highly malleable and ductile. Examples are the solid metallic elements. Here is a summary of the characteristics of the different types of crystalline solids, particularly their differences in the constituent particles, the interparticle force, and the general physical properties. Of course, many exceptions exist. For example, we have graphite, despite being a covalent solid, which is a poor conductor of heat and electricity, it has a relatively high electrical conductivity within the carbon planes. And diamond, it has the highest thermal conductivity of any known substances. This is the end of Module 3.1, Crystalline Solids. In the next module topic, we will focus and discuss fully the crystalline structure and properties of metals. If you have any questions and clarifications regarding the topic, feel free to contact your respective instructors. Thank you for listening and have a nice day ahead.